So, you guys are already working on your take home, on your rainy days. Good for you. Fantastic. Get them in on Wednesday, get the points back to you, for sure. I didn't get a chance to do the examograms either, like I did last time, where you have I had like the combined histogram of the entire class with the box plot, the box almost good plot. Again, because I was making rock and roll videos. So, wearing fur coats and stuff. Hot as hell, by the way. I can see how people do it. I used to be a militant vegetarian and vegan for a while. I think, oh, take your fur off, and I put the fur coat on. I'm like, oh, wow. It's actually quite warm. Anyway, let's stick with binomial momentarily. So what I've done here, and I'll have this posted. You don't have to write this stuff down. It's going to go kind of quickly, so don't worry about writing it down. So what I've got here is similar to Max and his Crocs are a number of binomial distributions that we know the probability is 1/2 on. I call it little p if it's okay with you guys. Little p is a chance of success. So flipping a coin, calling heads or tails. 50-50, arguably. Pulling a card out of a deck, getting a red or a black card. Assuming it's a poker deck, that's 50-50 as well. Gender, 50-50, arguably. I know sometimes people say women are a little bit higher than men, but it's arguably 50-50. So what I want to do is, I want to do the Max experiment, but I want to change the number of trials on the Max experiment. So first up, this is what it would look like if I only checked Max 3 times, as opposed to 10. So remember the distribution that Max looked like, 0 through 10. This is 0 through 3. And you can get these distributions in your TI. I mean, if you run distfill with a different number, 0 to 3 versus 0 to 10. And you can get the results. This is 12.5%. Which, hopefully this wouldn't be, you can actually tie this back to older probability, not even binomial. If you throw a coin 3 times, there are 8 possibilities. Heads, 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 tails, heads, tails, heads, heads, tails, heads. Forget it. It's too much of an annoyance. But one of the 8 possibilities is 0. 3 of the 8s are 37.5%, and then the last one over there is 12.5. And it's symmetric, just like Max's was, but it's more blocky. Suppose I watched Max 5 times, or pulled 5 cards out of a deck. It would look like that, yeah? Look like that. Now, notice, look at the ends of the distribution. Look what happened to the probabilities at the ends. I'm going to go back to this one. How many of you in this class are one of exactly 3 children in your family? One of exactly 3. Can I have the genders? Cheyenne.
2 girls and 1 boy.
2 girls and a boy. That's one of these 2 bars here. Jared? 2 boys and a girl. That's the other bar. All right. Now, I don't know how we're defining this as either number of boys or number of girls, but one of you guys is in this bar, one of you guys is in that bar. Who else? Rocks?
2 boys, 1 girl.
2 boys and a girl, so you're in with Jared. That's you guys in the same column.
2
Shelby?
boys, 1 girl.
2 boys, 1 girl, so there's 3.
3 girls.
3 girls. We're over here, we're over there. Good.
3 boys.
3 boys. There's the other tail. Look what you guys just did. Even with, oh, you guys just made a bell curve. I mean, think about it. With 6 people, you basically saw this distribution. And it's hard. It's hard to get into these tails because you have to flip tails 3 times, or heads 3 times for boys, or however you define it, not how you define it. Now, here's what it looked like for 5 children. Anybody one of 5 kids in here?
Thank God, no.
Go, Stace. Thank God, no. Stace, how many boys and girls?
3 girls. No, I'm sorry, I'm 6. 6 people.
Oh, you're 6. I don't have a curve for that one.
Never mind.
But you're 6. Is it 3 and 3?
It is.
Or
it
2 and
is
4?
3 and 3.
It's 3 and 3, which you would expect. If you have 6 kids, you wouldn't expect all girls or all boys. And you probably even wouldn't expect 1 boy and 5 girls. You'd expect 3 and 3 or 2 and 4 in some way. So we had some 5s though? Yeah. Was there a hand that went for 5? No, it's just Stace. Okay. So what's going to happen is, as the number of trials goes up, these tails basically fall away, which is predictable, I think. This is like flipping a coin. This is Max. This is Max's distribution. This is him always getting the shoes right if he's guessing, and that's him never getting the shoes right if he guesses. That should fall away. But what's interesting is look at the rest of the distribution. Okay? Look at the rest of the distribution. You might notice that these are getting lower probability-wise, which doesn't seem to make a whole lot of sense until you realize they have to. Why?
Because you have to add them all up.
Because you've got more and more bars, all of which have to have probability. So at the beginning, when they were 37.5%, then they went to like 32, and then 30, and then 28. Eventually, they have to drop down pretty low. Okay, there's 25, here's 50, and there's 100, and all of a sudden, if you look at it really carefully, there is a tail out here. You can have 100 coin flips and have them look them up heads. You can. But if that happens, what do you start thinking about the coin? That it's fixed, and that the curve for that coin should actually be over here, and not over there. That's when you start realizing, oh, Max guessed his shoes wrong 100 times? I don't think so. Or he has to write 100 times? I don't think so. I think he's getting them right because he knows how to put his shoes on correctly. So the point is that, what does that start to look like? What kind of shape is that now? Oh my God. We've been talking about this bell curve the entire class. Very informally, yes, where we say things like, oh yeah, it's bell, it's symmetric, it's shaped like a bell, it's unimodal. It actually is tied directly back to the binomial in that respect. They're one and the same, but we'll come back to why we're going to talk about this momentarily after I throw in this. Here's 100 randomly selected American women. I measured their heights. Actually, I did. The scientific journal did. I didn't have to, thank God. Look at that shape. It's not perfect like the coin flips are. But what do you notice?
Bellish.
It's bellish, is it not? We've got tails. We've got a dome right there. Yeah. Now, it's not perfect. We got a gap here. Maybe it's a little too tall here. Not to be perfect, though. It's bell-ish. It's bell-ish. Good. Heights. Men's LDL. You actually played with this one before back in the day, 4 weeks ago. Bellish? Noisy, but bellish. Noisy, but bellish. We're going to analyze this one in class soon, as in towards the end of today into Wednesday. IQs. 100. Bellish. Yeah? Bellish. Here's a few other things that if you look at them and study them, you actually get bell curves. Take a look at some of those things. Look how disparate they are. Like that one. Spans of refrigerators. This is interesting. Actual volume of a 15-gallon gas tank in a car. On average, it's 15 gallons, but there's a plus or minus around it. Like anything that's machined. Anything that's machined is going to have it's called a tolerance. That's why the ball bearings are that way. That's why the number of chips in Chips Ahoy cookies are that way. Yeah. Because there's a tolerance. You can't, unless you have one person actually dropping in 15 chips per cookie, which you couldn't afford. You couldn't afford to sell them at that point. Too much labor intensive. Too much labor intensive. That's why it's making that friggin' video this weekend. They're like, get somebody to do it. I'm like, we have no budget. I'll do it myself. Let's see. Time needed. What kind of data are you getting? Predominantly here. Predominantly, this is continuous data, isn't it? Did you catch the LDL? And the weights of American women? I think it was weights or heights, I forget what it is now. It was heights. Heights, LDL readings, which is a concentration measure. IQ, we'll come back to what IQ is, but it's also, these are predominantly continuous things. You can't deal with continuous data with a binomial distribution, but you can deal with it with what we're about to. And there's one last example I wanted to show you. I needed to show this to you. I used to have it linked in the, nah, it won't work. I used to have it linked in the PowerPoint, but it doesn't link anymore, so I will show it to you here. Oops, here it is. Yeah, just put it in there. If you've been to OMSI, you've seen this maybe. Yes! I went ape when I saw this. The way this works is awesome. There's a little conveyor. You can't see it because the screen's cutting it off. It drags the little tiny ball bearing, plastic ball bearings to the top, and it drops them right above the highest point of the curve, and lets them fall in. And there are tens of thousands of these little tiny plastic balls in the machine. Max is explaining it to you right now.
Oh my goodness.
At age 3, he already surpassed my intelligence level. And better hair, too, for that matter. But look, see what's happening. Now notice, there seems to be more in the middle and fewer on the sides. Okay, now Max, check out the far side. Now the way it works is right here they're trapped. Once they get to this point, they trap them and drop them in. But up above there's a series of pegs. So as the balls come down, they hit a peg and they either go right or left. What are you seeing, Cher? What are you seeing?
There's one that's kind of dipping below where I would expect it to.
Oh, any more?
I'll look at it,
But now it's not. This is a few minutes later. I decided you guys didn't go watch this for like 10 minutes. But look what's happening. This is the binomial distribution, but they're putting a bell curve on. There's my wife explaining it even better now. So there's, see, blink, blink, blink. It's math term. Blink, 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 blink. It's the game Plinko from Price is Right, is what it is. I mean, if you've ever seen Plinko, this is the exact same game, more complex. Oh, see them falling in right here, hitting the posts. Now you can see some are going all the way left and all the way right. But it's very unlikely for them to go all the way left or all the way right. Because in order for that to happen, it has to constantly take a right turn or constantly take a left turn. That would be equivalent to always flipping heads or always flipping tails. Think about it that way. That's not going to happen. More likely, you're going to get a balance of heads and tails. Now, a perfect balance of heads and tails puts you right down to the high point of the curve. A balance puts you right down to the high point of the curve. What's we got here? Any good stuff? There's me in a few years. A perfect balance, heads, tails, heads, tails, heads, tails, puts you right in the middle. You could get a run, as we've seen. You go tails, 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 heads, tails, heads, tails, heads, and that puts you off to the side a little bit. But in order to get truly off, unusually off to the side, you've got to go all heads or all tails. And as you saw from the video, it doesn't happen all that often. Does that make sense? So, another fusion of the binomial and the normal, which I find absolutely fascinating. All right. So, let's cut out of this. What I want to do is I want to shut this down, actually, for a while. And I want to draw some connections between this bell curve. And just so everybody knows, I can't explain perfectly why a lot of those things that show up on that one slide are bell curve, bell-shaped. I have a theory, and this is only a theory, and I don't know what it is. Anything that is the result of a lot of little intermediate steps will be bell-shaped. Kind of like those balls dropping in. Every time that ball drops in, it bounces off peg after peg after peg after peg after peg after peg. So each of those bounces is kind of like a step in a process to get from the top to the bottom. So think about like making a gas tank for a car. First thing you have to do is get the raw material, get the metal, bend it, weld it, bolt it, mount it, and all those things. And each one of those steps has either a left or a right. It can go high or it can go low, or stay balanced. So each of those steps kind of pseudo-randomly goes one side or the other, one side or the other. On average, it averages out and you're back in the middle where you should be. But then occasionally you get too far deviant and then far, far deviant, and eventually, that's a theory. I have no idea if it's right or not, and I have no idea of being able to, it's not my foot, it is, isn't it? But I have no idea if it holds any credence mathematically, but it seems to make sense. Like egg incubation times for chickens. Think about all the features, all the factors that go into making an egg in a chicken. The health of the chicken, the feed, the amount of water, the excess of range land that it has, its pecking order. There's all these variables that go into it. So what I want to start today, and we're going to spend the rest of the term in this distribution. We've got the binomial distribution. We like him. He's wonderful. Predominantly, the binomial distribution was used for discrete things. We surveyed this many people and asked them a question, and then we kept track of how many said yes. They can all be broken down to that. Or we bought this many pullets, and this is how many girls we got. It's all a chicken problem. If you could be a chicken problem, it's a binomial. And the reason why we like that is because it works really well for discrete data. And for discrete data, the distribution is going to look like this. It's going to have an x column and a p of x column. And generally, the x column starts at 0, goes to 1, goes to 2, and then goes to however far it goes. I'm going to call it n, if that's okay with you guys. It goes until it's done. It goes until you've measured every single possible random variable value that you can. And then you've got probabilities. I don't know what they are in this case because we're making this up as we go. But the sum of those probabilities always is what?
1.
Beautiful. Is 1. Sum of those probabilities is 1. And we can take the average of that, yes. We can find the average. We can get a standard deviation, all of which can be gotten from one of our stats or from formulas. There are formulas for these, but I don't make you memorize them because you don't need to. Okay? And that's the binomial in a nutshell. I mean, we just, in 30 seconds, synopsized what we did in a week and a half. But we understand that. What we now need is we need something that can deal with continuous data. And the beautiful part about continuous data is there are a whole bunch of distributions that will do the trick. In 244, we'll learn 3 more besides the one we're talking about today. Because you do need different ones to deal with different kinds of data. But the data I'll select for you and we'll deal with today does very well with what's called the normal distribution. Now, it's called the normal by definition. I'm not exactly sure where that came from. It's also called the Gaussian distribution, named after Carl Friedrich Gauss. Before Germany went to the, I'll show you this real quick. Before Germany went to the euro, they used the Deutsche Mark, Here's a picture of one. This is the 10 Deutsche Mark bill. Notice anything interesting on it? There's a bell curve on it. What does America do? America puts presidents, useless figureheads on our money. Germans put math on their money. Geniuses. This is why I often brag about being part German. Let's see. So anyway, it's called the Gaussian distribution sometimes. You guys call it the bell curve, which is great. But I want to get a little more deeply into the bell curve today and tomorrow and next week. That's where I want to kind of stay, because it's also where 244 springboards from. 243 wraps up with the bell, and then 244 springboards off with the bell. So it's a nice place to kind of wrap up. Here's the problem. Here's the problem. Because it's continuous data, it's going to deal with averages, which also have standard deviations. But the big difference is when you dealt with discrete distributions, you were just talking about percentages. How many out of how many? How many out of how many? How many? Well, that's easy. You count. You say, oh, I did it 12 times and I got 3 out of 12. That's a fourth. That's 25%. But here, it's continuous. So can we do this? For example, let's pick a random variable value. Call it 0. What's the next one going to be? If the data is continuous. Aren't there numbers between 0 and 1? Yeah. Not discrete values. It goes from 0 to 1. You can't have half a chicken. But can you have half a foot?
Yes. Yeah.
Or half a pound?
Yeah.
Can you have a quarter pound? A tenth of a pound? So my question is, what is the next number after 0 to the right? You can, it's infinitely close, so you can't describe it. Damn it! So what we don't do is we don't do that. Sorry. We don't do it that way. We have another tool instead. Here's the way and statisticians are very clever to do this. They don't deal with a t-table at all. Instead, they draw a horizontal axis like this. Number line! Like you used to use it. This is the same number line you've used since you were teeny tiny. And they make it infinite. Because technically speaking, continuous data goes off infinitely. Technically speaking. Now, very often we're going to limit the range of the data because you can't have, for example, negative 792 pounds generally, but that can exist. For example, when you're talking about heights of people, essentially it's got a low point at 0. But 0 technically shouldn't even be on that graph because nobody's 0 inches tall. I mean, even embryos have a height, right? Nobody's 0 inches tall. So 0 would be asymptotically not possible. So you'd be way, way down here. But for purposes of illustration today, I'm going to put 0 right here in the middle. This is a unitless figure. It's not 0 somethings. It's not 0 pounds. It's not 0 ounces. It's not 0 feet. It's not 0 seconds. It's just the number 0. And I'm going to call that the average. I'm going to call that the average. So here's the deal. The normal distribution is a little bit different than the binomial because before you start, you have to know what the average and the standard deviation are. Before you even start, you have to know what they are. Whereas the binomial, you get them when you're done. You have to start by knowing them here. And this will make more sense as we go, I promise. Serena's looking at me like, what the hell? Totally, I'm with you, sister. But you are going to understand the only way you can construct this curve is if you know these things. So bear with me. Give me 45 minutes.
So you need the standard deviation
and the average. Now, there are different normal distributions, but the one I want to talk about today is just the most basic, and it's the one we're always going to come back to. It's the one I built a program for you guys for. We're going to get to that today, too. It's called the standard normal. It's called the standard normal. And the reason I like the standard normal is because we can convert any other bell curve back to this one. We'll show you that skill on Wednesday. But the standard normal has an average of 0 and a standard deviation of 1. The reason I like this one is because it applies to just about everything. For example, my 244 class was just analyzing weight change in anorexic girls. This is a really interesting study done at the University of Psychiatry in Britain. I think it was 36 or 38 anorexic girls went on to a weight gain program to try to help them gain weight back that they had lost throughout their anorexia. And they wanted to see if a program was effective. So what they did was they weighed the girls before the program, before they started, then gave them this 6-month intensive program of weight, and then measured them a second time, and then compared their weights before and after. If there was no difference before and after, the difference in their weight would be 0. That's why I like this curve. We can do those kinds of before-after studies beautifully with this. So if there's no change, the average change is going to be 0. Some might go up, some might go down, but if it averages to 0, that's where it's going to be. Now, the standard deviation is squirrely. So for right now, bear with me and just call it 1, because this is what it's defined to be. If anybody's interested in why these are 0 and 1, on the enrichment page of your website, I've written down a formal proof for you. If you're interested as to why the 1 shows up and why the 0 shows up, it's all there for you. If you care. You don't have to care either. Take my word for it. But what that means is, we can now slap values on the curve like this. -1, -2, -3, and then -4 will be down here. And each one of those numbers indicates a standard deviation. So 0 is average. So when you go up 1, you're now at the top end of a standard deviation. -1 to 1 is that critter we called 1 standard deviation back in the day. -2 to 2 is the critter we called 2 standard deviations back in the day. So what I'm going to do right now is, I'm going to draw the curve on top of this. But the one thing I have to kind of apologize for, I don't know why they do this. These aren't called X's. For some reason, in the standard normal curve, they're called Z-scores. And you may have heard this phrase before. I mentioned it weeks ago, because your book teaches you that right in the beginning. And I said, we're going to skip this right now. It doesn't make a whole lot of sense until we get here. So these are actually Z values. They're called Z-scores. That's the variable that has come along down statistics history when you talk about a normal, standardized normal distribution. They use Z-scores instead of X-scores. When they talk about general normal distributions, which we'll talk about on Wednesday, they bring the X back. But this standard one here, the standardized one, you remove the units. When the units go away, they call them Z's instead of X's. So we'll get used to it. Don't worry, we call them stud normal over here in the program. We'll get back to that as well. So this line corresponds to the X column in the discrete distribution. What's going to correspond to the P of X column? Where's the P of X going to go, do you think?
Up and down?
Yes, up and down. We're going to add, exactly you guys, we're going to add another axis here, which is going to be the probability axis.
Or Y, right?
Or Y, exactly. Can I call it probability? Because that's what I want to kind of drive into your, or Y, exactly. This is also X and Y. Exactly. So probability, or Y. Oh, you're thinking Math 111. You are, John. It's good for you. F of X.
Try not to.
Try not to. Sorry, I'll stop talking about it. So this is going to be your probability axis. So here's the deal. Essentially, each value that's on this horizontal has a vertical value that indicates its probability. Just like those curves we showed you earlier as we kept letting the sample size go up and up and up and up and up. When the sample size goes off to infinity, you're going to get a smooth curve. If you guys are taking calculus, so this will ring a bell. So the most likely value is going to be what, do you think? 0, because that's the average. Now you don't have to know this. The value that it goes up to is, I think it's 40% or something. It's not important to know that. I'll explain why momentarily. What's going to happen as we get further away from average? They're going to drop off to either side, and over time it's going to form the bell curve that we know and love. Now the reason it's this shape is due to its mathematical equation, which I'm never going to make you memorize because it's not worth memorizing. It's wonderful. It's wonderful. And it's actually on that that 10-mark bill from Germany. The equation's actually right there under the curve, which is cool and beautiful and wonderful, and I love the Germans for doing that. But the important thing is not the equation. The important thing is understanding about the graph of the result. It's perfectly symmetrical, even though I didn't draw it perfectly symmetrical. If you put a dotted line through average, the left and right sides are equal. But we already knew that from talking about it weeks ago. I tried to prep you for this weeks ago by constantly bringing it back. You know some other stuff too, don't you? About the bell curve. We do mention it frequently. When we get bell curves, the average and the median and the mode are all the same, as we can indicate by this. Half of the curve is on this side, half of the curve is on that side. We know that as well, right? What else do we know about the bell curve? Give me some more information that we know from back in the day. Oh! Say that again.
95% of the data is going to be
95% of the data is going to be within 2 standard deviations. On this curve, what does that mean? Between what and what?
2 and 2.
Between 2 and negative 2. Now here's where I need you to understand something. This is where technology has to help us out. I didn't draw it very symmetric because it's way skinnier on this side than it is on this side. We'll deal with that momentarily. What does it mean to be between negative 2 and 2? Well, at negative 2, there is a probability, and it would be that right there. And I don't know.
Drop the cap.
I dropped the cap, like I always do. I don't know how tall that is. I mean, it's got a height over here. I don't know what it is. 2 also has a probability. Now, ideally, if I had drawn this correctly, they'd be the same height, because they should be the same height, because it's symmetric. This is why we don't draw this one, and then we let the TI draw the rest of them for us. But in order to calculate all the probability, all the percentage, that 95% between negative 2 and 2, I'd also have to add up all the other probabilities of all the other z's between negative 2 and 2. So I'd have to get negative 1. I'd have to add up 0. I'd have to add up positive 1. What else would I have to add up? What other numbers? Give me some other numbers in there. Throw them out. Call them out. Be louder. I'm a punk rock drummer. I'm deaf.
1.5.
1.5. Another one. 1.75. Another one. 0.5. Another one. Negative 0.5. Another one.
Infinite.
It's infinite, isn't it? Because I've got to get 2. I also have to get 1.9. But I also have to get 1.91. But that means I have to get 1.905 and 1. And this gets ridiculous, doesn't it? So what did you do in geometry class when you had to talk about that whole area? What did you do with your pencils? Fun. You did this. And you kept shading. And shading. And until you got the thick shading. And the reason this works is, we know it's infinite, but we also know, assuming that I colored it better than I did, we just covered the whole area, didn't we? We covered the whole area. Now mathematically, this is a slight bit tricky, because mathematically, you can't just color. You have to derive an equation, and you have to use the equation to get these values. And what mathematicians do, and this is pretty slick, I'll give you a brief introduction to integral calculus. What they do is, they take the region from negative 2 to 2, and they say, break it up into 100 smaller regions, and then draw a rectangle that ends up on the curve. Draw a rectangle that ends up on the curve, draw a rectangle that ends up on the curve, and then they add up all those rectangle areas. A rectangle area is easy, right? Length times width, length times width. Add up all the rectangles. Problem, of course, is you've got some overage there, right? So how do you minimize the overage? Make the rectangles skinnier. Instead of making 100 rectangles, make 200 rectangles, which means they'll fit better. Instead of 200, make 1,000. Instead of 1,000, make 2,000. And the problem with that, of course, is that if you're not using a machine to do it, FYI, everybody does nowadays, but if you're not using a machine to keep track of that, that becomes very labor intensive. But everybody uses the machines nowadays. I remember going in, I was building a deck on our house about 5, 6 years ago, and I wanted to figure out if I needed to use 4x12s or 2x12s for this one span. And I was in the hardware store, and I'm like, oh crap, I didn't figure this out. So I take it out, I can borrow some pencil and paper, and I start taking computations. He's like, what are you doing? I'm like, I gotta figure out if I needed 4x12. He's like, dude. And he spins a computer around, and big sheet comes up, has the answer for me. I'm like, well, okay, feeling pretty old right now. But that's the point, is that these kinds of computations can be done manually, but nobody does them manually anymore, because if you understand what's going on, it's not important to actually do this plus this plus this plus this, because you screw it up. So, and you know what the answer is already, Patrick gave it to us. It's what? It's 95%. We know it's 95%. Now here's the question. What if I went from negative 1.5 to positive 1.5? What would that be? Don't answer that yet. Don't answer that yet. We'll come back to that question. What I want to do is I want to show you one of the other gifts I gave you. Grab your TIs again. Because this question right here leads us into another program that I wrote for you. So if you fire up your machines, if you look in that machine, you'll see one called Normal. Grab that one now. As much as I like dist fill, I'm the proudest of this one. I think this one came out the best. The first thing it asks you is it a forward or is it a backward problem? I've made up these terms. I've never seen them in a book before. Here's how I define them. Here's how I define them. A forwards problem is one where you know the z-scores and you're going for the areas. So in other words, Patrick said 2 standard deviations. Those are z-scores, -2 to 2. And then he said 95%. So we knew the area already because we've been talking about it. But suppose you didn't know what it was, right? Suppose you didn't know what it was. Let's suppose you needed to know what the percentage was. So you'd call that a forwards problem. We'll do some backwards problems later on today to compare and contrast. Forwards problem. The next couple things I asked you, are we doing between, left, or right? This one's between, because we're going between -2 and 2. Does everybody find this okay? Everybody found the normal, we're getting, Andrea, we good to go?
Go.
Program?
Yeah. Forward and backward. Can you repeat that really quickly?
Forward is when you have the z-scores
Yeah.
on the axis and you want to know what the area is between them.
Okay.
And then backwards is you have the area and you want to know the z-score. We'll come back to those
So
momentarily.
we're doing
Cool,
forward.
thank you.
We're doing forward right now. Yes, yes ma'am. Forward, right now we're doing a between. Between. If it's a left, it's got a left bound and a right bound between which you're going. So put in -2 for starters. And then put in +2 for the endpoint. And then press enter and it will draw it for you. And it'll shade it for you. And then at the bottom right corner it'll tell you what the area is. This is much better than trying to draw it. And because as you can see, I drew it horribly skewed over there because I had the curve too far to the right. And also, the beautiful part about this is you can actually see it shading as it's going. It's keeping track of all those little tiny infinite rectangles as it's going. It's doing the calculus for us. What's funny is when I first wrote this program, I told a bunch of my stat colleagues around the state I was doing this, like, oh my God, you're not making them use normal tables? Because the way everybody else does this, except for a handful of people, is there's all this, they have tables that is in your textbook somewhere. I'm sure there's a normal table where you have to go and like look up the number, like you put the z-scores in and go look the numbers up and subtract them. And if you don't have technology, that's what you do. But we have technology, and it's funny because people were saying, well, that's cheating. I said, no, it's not. They said, you have to use the normal tables. I'm like, you're cheating. The only way you're not cheating is if you're doing calculus. And that's dumb, because nobody does it anymore. So let's cheat together. Cool? So now you've seen this number before, that's 95%. How about 1 standard deviation? You know what that is, right? We know what the answer is going to be from before. It's about 68, about 2/3. Press enter. It says, are we going to go more probabilities or we're going to quit? Let's do more probabilities. I couldn't put that on the binomial program because you have basically at the binomial, as soon as you're done, you have to go out and look at stat lists. So I needed to end the program right there. This is why I like this one. You can keep it cycling. Forwards again, because we know the z-scores. -1 to 1. So it's between -1 to 1. That number look familiar? Heck yeah. There's your roughly 2/3. What's also cool about this is, you probably never thought about this before, but if you know that's about 68%, what's right there? Half of it, 34%. How about here? Additionally 34%. Now, if you're not making that connection yet, you don't have to. That's the best part about this program. More probs, forward. Start, go between. Start at 0 and go to 1. And it'll shade, starting at the average and going out to 1 and tell you it's 34. Half of what it was before. So you don't have to keep that in your head if you don't want to, but it's nice. Renee, go, please.
So you're counting standard deviation?
These numbers, thank you for that.
Well,
These numbers down here are the numbers of standard deviations.
okay.
So 0, 1, 2, 3, and so forth. -1, -2. That's a beautiful point, and it can't be made enough. When you're on the z-axis, those numbers, 1, 2, 3, 4, those are numbers of standard deviations. That's a humongous point to make, and go ahead.
So the z-values are standard deviation?
The z-values are the numbers of standard deviations away. A 1 is 1 away, a 2 is 2 away,
And
a 3 is...
that's how they're useless.
Yes, because it's strictly standard deviations. What we're going to learn to do on Wednesday is convert back and forth between units and unitlessness, because we have to be able to compare everything to this curve that we already know. Like when I tell you that I got someone with an IQ score of 85, you've got to know what that means. We'll come back to that momentarily. But yeah, this is good. Did you remember hear when they said it's awesome? These numbers are standard deviations. The further you get from average, the more unusual that is. And you can tell that by the curve falling off. By the curve falling off. Is that fair? So here's another question. Thank you, Renee. That's a very, very good point. Very, very good point. Here's another one. Suppose I want to know what is the area to the right of positive 1. This would be, for example, what percent of the data is outside above 1 standard deviation. Now, can you use the TI to do it? Yes. Could we get a ballpark of what it has to be based on the screen we currently have on the board? I think we can. How can we use what's on the board to figure out what that has to be approximately? I'm talking about ish. Danny, go ahead, go ahead.
50 minus 34.
What Danny said is, well, I know this is half the curve. And 34% of it is here. That means 16% of it has to be out here, yeah? That's fair. Now suppose you don't see that. It's okay. I wrote the program for you. Go back again. More probs? Yes, let's. Forward? Yes. But this is now a right shade, because we're going to shade to the right of positive 1. Yes?
Oh, okay.
Yes, so we're going to right, and then it asks for a left bound. Let's start at 1, and go all the way out. It's going to start there at 1, and there's your roughly 16%. Yeah? Let me ask you another question while we got this screen up. How about down here? What would that be?
The same.
Wouldn't that be 16% as well? Because the curve's symmetric. Same side on both, same shape on both sides. So that would be a left shade, should you choose to do it forward. Should you choose to do it forward, you do left, right bound -1, and you get 16. Is that fair enough? Good, decent? Decent. So that's how the forwards problems work. The forwards problems are when you have a z value and you want the area. Now here, this comes back to, remember how I said when I was shading my curve over there, I said, once you're done, you've covered all the region. You've covered all the region. So you know you've covered all the possibilities. The reason why it doesn't matter is, I will never ask you a question like, what's the chance a randomly selected adult American is 5'11"? Adult American male is 5'11". I will never ask you a question like that, because it's impossible. Nobody is ever exactly 5'11". This is continuous data, right? You can't be exactly 5'11". Your height is, first of all, your height's changing constantly. Secondly, whenever I ask you guys what your height or what your weight or what your age is, we always round things off, right? I'm 5'11 and a half, I'm 175 pounds, I'm 40. I'm not 40, I'm more than 40 years old. I'm not 175, God only knows what I am right now. I'm not 5'11 and a half, I've been up for 8 hours. I probably shrunk quite a bit because gravity's pulling me down. So what I will ask you are questions like, what's the chance a randomly selected American man is between 5'10 and 6 feet? That's a different question, because what we'll do is we'll shade between two values and capture that whole likelihood. And if we want to get more precision, we just move them closer together. But we never make them equal to each other, because that point is meaningless. That point is meaningless. It has no meaning. Does that make sense? This is the beauty of this. All we got to do is adjust the values that we're selecting. Cool? Those are forwards problems. So can you think of a backwards problem? I shouldn't have done that. I'll put the numbers back up momentarily. What would a backwards problem look like, do you think? You've done them. You've done them a lot here, actually. I've made you do them because I'm a total jerk. I've made you do lots of backwards. I made you do one of your last exam you guys just got back. The first few questions were backwards. Stacy?
When we had to find the missing item in the PX list or whatever, that's a backwards.
Oh, believe it or not, that's not.
No?
It looks like it is for the binomial, but it's not for the normal. I would never do that to you in the normal, because there are infinitely many probabilities. When Stacy's thinking of the last question on your last in class, when you had to put the missing probability in the bottom, that little gap that was there, that was a backwards problem for the binomial, but I would never do that to you here because there's too many to keep track of. Thank you, though. Very, very good.
Was the question where you were like, what's the percentile of 32,094?
Yes. So here's the deal. You can make percentile rank problems forwards or backwards. If I say, what is the percentile for this amount of, I think it was salary on your exam, I forget which data set I used. Oh, here it is.
There we go.
Expenditures. If I ask you, what is the percentile? So the first question, find P40. Find P40 for annual consumer unit spending. That's a backwards problem. Because I didn't tell you the raw data value, I asked you, what's the 40th percentile? So in other words, I've given you a percentage, haven't I? So let's do that for the normal curve. What's the 40th percentile for the normal curve. Now, first of all, where do you think it will be? Here's 0, remember, I'll put 0 right here. There's 0. Where do you think the 40th percentile will be compared to 0? First of all, what's 0? What percentile is 0? Let's agree on this right now. What percentile is 0? Be brave. It's the 50th percentile, isn't it? Why? Let's remind ourselves of why. Because it splits the data in half. It's the data point above half the data. If you don't believe me, let's use the program to convince you. Press enter. More probabilities. This is now your first backwards problem. Backwards. Okay? Okay. Which we're going to shade, let's shade left for percentiles, yes? What percent do we want to shade to the left? 0.5 for 50th percentile, yes? 0.5. Here we go. Here we go. Z-score, 0. Boom. 0 is the 50th percentile because you shaded half the scores. So my question for you again is, where's the 40th percentile? Where would it have to be? But before you, good. Answer's already going. More probabilities. I got this right now. Logically, where does it have to be compared to 0? It's got to be in one of the negative ones, doesn't it? Because it only has to exceed 40%, not 50%. Good. So, continue. More probs. Again, backwards. We're going to shade to the left.
Negative 0.25.
0.4. Very nice. Here it comes. Isn't that amazing? Negative 0.25. Now remember, try to wrap your mind around this mathematically, because this always blows my mind whenever I see something like this. The entire curve is 50%. That entire half of that curve is 50%. 10% of that 50% is a little tiny sliver right there. Isn't that amazing? That means this is 4 times as big as that. Doesn't it look more than 4 times as big? Isn't that incredible? It looks more, to me it looks more than 4 times as big, but mathematically it's exactly 4 times as big. But that's how close, that's how tall the bell curve is around the average. That's why the normal values have a very tight standard deviation. The further you get away, exponentially, they get more unlikely. Let's find an old friend. We know what this is now. See why it's a backwards problem? You got the area, and now you tell me it's z-score. So the 40th percentile is negative 0.25. That might correspond to $32,000 from your in-class exam if those data are bell-shaped. I'm not sure if they are or not. I didn't actually get the raw data from the BLS. Yeah, purely statistics. Let's do an old friend, shall we? Old friend? Q1? Shall we? Yes? I'll answer for you. Yes? More probabilities? Backward? Yes, ma'am. Shade left? 0.25, yes. 0.25. Check this out. This might be even more mind-blowing for you. Negative 0.67. So 2/3 of a standard deviation, yes? 2/3 of a standard deviation. How much area is right here?
25.
That's 25%, isn't it? If this is Q1, that means 25% of the curve is shaded right there. That means starting at negative 0.67 and going down to infinity is 25% of the curve. The next 25% of the curve is only between negative 0.67 and 0. Which means the next 20, I know Cheyenne's like, this is ridiculous. It is kind of crazy to wrap your head around. Which means if I go up to positive 0.67, what do I got there? The next 20, there's Q3, yeah? And you could run it as a backwards problem and do shade left 75% to figure this out. We don't have to because we know it's symmetric. And then 25% here. Isn't that wild? That's crazy to me. Go, Renee.
It doesn't matter what the bell curve looks like, it's always going to be like that?
The bell, very good question. The standard bell curve always looks like this. General bell curves can be shorter and wider if they have a larger standard deviation, or taller and skinnier if they have a smaller standard deviation, all of which we're going to mess with starting on Wednesday. But the standard bell curve is always going to look just like this. The good news is we can always convert down to this one from the other. That's the beauty. That's what we're going to deal with on Wednesday. So as long as we can familiarize ourselves with this right now, though. And this is where it blows me away when I think about psychology classes. They teach you guys 1, 2, and 3 standard deviations. I think they should teach you 2/3 of a standard deviation. Can you see why now? Why would 2/3 of a standard deviation make a whole lot of sense? That's 2/3 of a standard deviation, yes? 0.67, 2/3. How much data? Half. Such a logical number. It's the number indicated on your box plot, yes? Your box plot, half of your data is within 2/3 of a standard deviation. I don't know why they don't teach that. 68 is great because 1 is a nice number, but half is so much more logical. Half your data is between 2/3 of a standard deviation. It's crazy. It's totally cool. So those are backwards problems. You can also, should you choose, you can also run these shading to the right. So I did this intentionally. If you go back and run one more backwards problem, you can also shade to the right. You can also shade to the right. And you would put it, so for example, on your exam that you guys just did, I asked you, I said, what percentile is $94,500? It was a bit of a bastard question because it said on the exam that 20%